So imagine we have this function f of x equals 5e to the 2x. And we wanted to calculate that, say at x equals 0.8. However, it's not immediately clear how we could do that with basic multiplication and addition, because it's easy to take a number to an integer power, but when you take it to some fraction, it's not quite as clear how to do that. So one way to do that is we could approximate this function 5e to the 2x as a polynomial near x equals 1. And that's basically what a Taylor series is, and that's kind of why you need something like a Taylor series for your calculator to calculate a value for a transcendental function like this, because it may not be apparently clear how to calculate this when x is not an integer. So if we went ahead and plotted out this function, and our goal here is basically going to be, we want to find approximately what this is here. Initial first step here would just to be to make sure, let's make sure these values are equal here. When x equals 1, that's easy to calculate here because that's going to be an integer. Let's make sure these are going to be equal. So we take our polynomial, and we'll just call that p. So we'll say p of 1, let's make that equal to f of 1 as a start. And that's pretty easy to find. We just plug in 1 right here for x. And so our f of 1 is going to be 5e squared. So we're going to make that our p of 1 also. Now if we want p of 1 to be 5e squared, let's just make that p of x. So let's just say p of x is equal to 5e squared. And this is going to be our 0th order polynomial. And if we plotted this out, it's not going to look very fantastic. It's just going to be a straight horizontal line. And it's not going to get us very close down here to where we wanted to find it at 0.8. But hey, it's a good start, right? I mean, we're right on right here when x equals 1. But of course, we can do a lot better than this. And the first thing you may guess is how we can get better is, rather than just having that value equal here, how about we have this actual slope equal here too? So instead of this horizontal line, what if we still had a line, but but we had the slope of that line was actually the same as our function. So this is basically linearization, which you may be familiar with. In order to find that, all we got to do is we just want to take p, and we want to set the derivative of p at 1 equal to the derivative of our function at 1. So in order to find that, we just need to find the derivative of our function. Using the chain rule, we get 10e to the 2x, and we want to find that evaluated at x equals 1. So again, when we just plug in x equals 1 right here, we just get 10e squared. So that's going to be our p prime of 1. And we're going to write f prime of 1 up here just because we want to kind of keep track of it for later. And now, if we want p prime of 1 to equal that, let's just make p prime of any x value equal to that. Well, that's because that's an easy way to make this function. So we'll say p prime of x is equal to 10e squared. And if that's going to be our p prime of x, now we're getting pretty close to finding our first order polynomial representation of this function. And the first thing we do for this is we're just going to take down our piece of 0 of x and make that our first term here. And now we know that the derivative has to equal 10e squared. So if we want the derivative of this function up here to equal 10e squared, well, then we could just add in another term, plus 10e squared x. So imagine we take the derivative of this with respect to x, we're just going to get 10e squared. However, imagine if we wanted p sub 1 of 1. So if we just say x equals 1, we get 5e squared plus 10e squared. And that wouldn't equal our f of 1 anymore, right? Because we want our f of 1 to equal 5e squared. So to address that problem, all we got to do is, instead of x here, we can just call that x minus 1. And that means that our p of 1 will still equal our f of 1, which we want because we want these points to equal right here. And when we take the derivative of this, you could imagine we take the derivative of this whole thing right here, we're still going to get this right here. So that making that quantity x minus 1 solves that problem. So this is going to be our p sub 1 of x, our first order approximation, which is shown here in the blue line. And you can see that we're matching the value right here, but we're also matching that slope as well. So if we wanted to evaluate this function, get something close to this function at x equals 0.8, you can see we were pretty far off with the red one at this point, but with the blue one, we're getting a lot closer. We're not quite there yet, though, and we can do better. And how we can do better is, instead of just doing it sort of a linearization, we can sort of do this linearization on steroids, if you will. Instead of just making sure we get the right slope here, we can make sure we also have the right slope of the slope, or we have the right concavity. So we get this sort of the bending effect here. And how do we can do that? Well, we can just make sure that our second derivatives of our polynomial and the function are equal at x equals 1. So we want to set p double prime of 1 equal to f double prime of 1. So we find f double prime of 1 up here, and we evaluate that at x equals 1, and we just get 20e squared. So let's go ahead and write that up here for later. Now if we want p double prime at 1 to equal this, we can just make p double prime of x equal to that for any x value. So that's going to be our p double prime of x. And if we want this to be our p double prime of x, well then now we gotta kind of work back up and make sure our p prime of x is right. So our p prime of x is we're gonna want to make that the integral of our p double prime of x. So if we integrated this up here, of course all we got to do is throw in that x term on the end, and that's our integral plus a constant c. But you can imagine if we did have this 20e squared x term, if we went up here, our f prime of 1, if we added that term on there, we actually get a plus 20e squared, which of course we don't want that, right? Because we already calculated that this slope here, we want it to equal 10e squared. We don't want to add this plus 20e squared term on here. So for the same reason we found before, instead of making this x down here, we're going to want to make that quantity x minus 1, and that gets rid of this problem that we had up here. So if that's our first derivative, then we can get back to our initial function by taking the integral of that again. And you can imagine if we take the integral of this, we're going to have to use the inverse power rule, so we get this 2 on the bottom. And then this x minus 1 quantity becomes x minus 1 squared. So now we're ready to calculate our second order term, and that's going to be this. We keep the same thing we had from our first order term, but now we're going to go ahead and add this down here, so we can make sure that our second derivatives are going to equal each other. So we just go ahead and throw that in up here. And if we plot this out, we can show this in purple now. It's actually getting a bit closer. So this is the point we're trying to look at right here when x equals 0.8, and the red was pretty far off. The blue was a lot better, but now the purple is even closer. So we can see we're getting better and better as we match first, second, and third derivatives. We're getting a lot better. And well, we haven't really done the third derivative yet, but we could, and that would actually be a much better approximation. So this would be our third derivative of f of x using the chain rule. And if we evaluate that at 1, we just get 40e squared. So if we wanted the third order polynomial, we would just use what we had before, but now we're going to go ahead and add in this third term. And in this case, we have the 2 on the bottom from the inverse power rule, but we also have this 3 because we had to use the inverse power rule one more time because we had to integrate. We matched the third derivative, and we had to integrate 3 times to get back to our function. So we ended up with this 3 on the bottom and the 2. Now, we could go ahead and claim victory here for what we're trying to do, because this is going to be a pretty good approximation. But what we could also do here is just try to see a pattern that is developing. Just to help illustrate this pattern a little bit better, we could also say p sub 3 of x is going to be equal to f of 1 over 1, right? Because our f of 1 was just 5e squared. And I'm just going to divide by 1 here just to help clarify a pattern. In our next term, we just had this f prime of 1 on the top. Again, divided by 1 to make the pattern clear. And of course, this time we had to multiply that quantity by x minus 1. In our third term here, we just had our second derivative, because we had this relationship, right? And except this time now we're dividing it by 2. And then we're going to multiply that by the quantity x minus 1 squared. And for our fourth term here, based on this equality, we've got our third derivative evaluated at 1, divided by 2 times 3, and then multiplied by this quantity, x minus 1 cubed. So hopefully now that you can see the pattern is becoming more evident, and we could actually write this down as an infinite series. Down here we've only gone to 3 terms, so this is still approximation, but if we went out to an infinite number of terms, this would no longer be an approximation, it would be exactly f of x. And we could say f of x is equal to this infinite sum, And now you can see the first term here is going to be this x minus a to the n. And in our case, a was equal to 1, which is where we were centering our approximation at. And as you can see, when n equals 0, our first order term doesn't have that x minus 1. But our second term, when n equals 1, it's got this. And when n equals 2, we got it squared. N equals 3, it's cubed. So you can see that we can see a pattern there developing. You can also see the pattern pretty clearly when we show these derivatives like this, because this is the 0th order derivative, the 1st order derivative, the 2nd order derivative, the 3rd order derivative. And we can go ahead and denote that on the top here by f parentheses n, where that parentheses n just means the nth order derivative of our function f. And now lastly, you can see on the bottom, so this 3 times 2, you can just imagine a 1 right here. And you could say that, well, this looks like 3 factorial, right? And this over here, you could imagine a 1 here, and you could say, well, this looks a lot like 2 factorial. And this would just be 1 factorial. And this would actually be 0 factorial. So you could also see the pattern here developing on our denominator on the bottom, where we have that n factorial on the bottom. And again, just to summarize, this is the Taylor series, and it gives us a polynomial approximation of a function. All we really need to do in order to find this is we have to be able to calculate these derivatives of the function. If we can calculate the derivatives of a function, we can get to its Taylor series polynomial. And for a lot of cases, this is very useful because it's a lot easier to deal with polynomials than it is with some complex transcendental function.